So in this video, we're going to be learning about continuity of a function at a defined point or in an interval or different types of discontinuities. So first off, let's talk about the definition of continuity here. So a function is continuous at a point provided the following conditions are met. So it's defined, the limit exists, and then that limit value is equal to that defined value. Okay, so we need to show this work. Whenever we are asked to find if something's continuous, we need to show all of that work. Okay? Something that's continuous, by the way, is like a function like this. As I was drawing it, before I did the arrows, didn't pick up my pencil. So that's one way to think of something that's continuous. A function's continuous if you can draw it without picking up your pencil. So let's talk about continuity just on an interval. So a function is continuous in an entire interval, closed interval from A to B. If it's continuous between the interval, and it's continuous on the edges of the interval. That's why it says it's continuous from the right of A, so it's just continuous just to the right of that, and continuous on just the left of B right there. Okay. Now let's talk about something's not continuous. So I'll draw these examples as well. So removable, that's the same thing as a hole. Okay, so removable would be if I have a hole in the middle of my function. So the limit does exist there, but in order to draw this, I'd have to pick up my pencil. Okay, a jump would be something like this, where I jump up to keep drawing it. An infinite is going to involve an asymptote. So this is an example of infinite, because an asymptote would stop you from drawing it, and you need to pick up your pencil. Alright, now let's move on to some examples. Let's determine whether the following function is continuous at x equals 2. So I do need to show those three steps. So first off, I need to show that it's defined. So I'm going to do h of 2. And let's look at this function real quick before I get too ahead of myself. It's kind of weird. It's a piecewise, but it's going to be, it says it's 4 only at 2. But everywhere else, it's this function right here. Okay, so when I do h of 2, I got to plug in a 2, which is going to be the top or the bottom. That's right, it's the bottom because it's only is 4 at that point right there. So this is equal to 4. So far, so good. Two more things I got to do. Second one, I'm going to kind of do this a little bit of side work for this one to find the limit. So I need to make sure that the limit exists, which means I need to show that the limit as x approaches 2 from the left is equal to the limit as x approaches 2 from the right. I need to show this. Can't just write that down without any work. I have to actually go through with it. So when I do this, since I'm finding the limit as I'm going just to the left of 2 and just to the right of 2, I'm actually using this top one up here. Because let's say that I'm picking like 1.9. If I find the x value of 1.9, I'd use the top. And likewise, if I go to the right, like 2.1, I'd have to use the top. So I'm looking at just the top function right now. Okay, so real quick, that top function can actually simplify for us, because this can factor to x minus 2, x plus 2, and these are going to cancel out, and this is actually going to be x plus 2. Okay? This is actually x plus 2, but it's got a hole. It's got a hole at x equals 2, which is totally okay because, well, this piecewise function is defined at that. So for this, I have to plug in a 2. So I plug in a 2, I get 4. Plug in a 2 for the right, I still get 4. So this does check out. So this does work. I'll put a check mark up here, say yes, it's defined. Now I need to show that the limit as I approach 2 is equal to h of 2. Well, we just said that both these values are equal, and what are they? They're equal to 4. So the limit is equal to 4, the defined value which I'm using this bottom one here too, is equal to 4. So this equals 4. Boom. So therefore, h of x is continuous at x equals 2. So those are the three things I had to show for that example. And then next one, we're going to find the value of x at which the given function is discontinuous and identify the discontinuity. So we don't need to go through the steps 1, 2, 3. We're just going to figure out where it's not continuous at and what type of discontinuities there are. Okay. So, but for these though, we got to make sure that we are in the domain. And I really only have to worry about that if I'm looking here in this guy right here. Okay? Because the domain of any square root function is that this needs to be greater than or equal to 0. In which case, if I were to factor this, I get x minus 3, or 3 minus x, 3 plus x, 0. Quick little chart here. Negative 3 and 3. So this needs to be greater than right here. So my domain for this function is just from negative 3 to 3. Okay, so if I find if I find like a discontinuity outside of that domain, it doesn't matter because it's not really it's not part of the function. This is kind of what we did speaking to this continuous on this interval. So yeah, this function cannot be like 4, but it's still continuous on the interval because there's no value that you can choose in which that you cannot use that is on the actual domain itself. Okay, so this is continuous on the domain. There's no holes, no asymptotes, so this one's good to go. It's continuous on its domain. Next one, a couple things going on here. You got a denominator to worry about, and that's usually where something weird is going to happen here. So what I want to do here is I want to factor this. Top factors to x plus 3, x minus 3. Bottom one factors to x minus 2, x minus 3. So I usually want to find my holes first. So these right here, I'll do it in green, cancel out, which means that I'm going to have a hole at x equals 3. Again, you just set whatever you cancel, set equal to 0. And then the denominator here is going to give me an asymptote. So we're actually going to have an asymptote at x equals 2. So that's to get a little more technical here. Where are my discontinuities at? Well, I have a discontinuity at x equals 3, and this is removable. And x equals 2, which is infinite. Alright, so this example is going to kind of bring both of the previous examples together. So we have arctan of x plus ln of x over x squared minus 4. So these top ones right here, they are continuous. It's nice to know what these graphs look like. Arctan looks something like this. And then ln of x looks something like this. So they're continuous over their domains, but then I have this on the bottom here to worry about as well. So a lot of people just think that just solve for the bottom and done, but we have to find the domain of this first because this can get a little weird with this ln of x especially. So let's find the domains real quick. And the reason I'm finding these domains versus this one is we've done a lot of these problems. Top is a polynomial, bottom is a polynomial. Domain is fine in terms of the interval. So let's find this domain. So for the arctan, left to right, it can be anything it wants. So the domain is all real numbers. The ln of x domain, that has to be between 0 and infinity. It can't be any negative values or any 0 values. Okay? And for this x squared minus 4, that's going to be all real numbers as well. So I'm looking for the domain at the top and the domain at the bottom. So my answer has to be between 0 and infinity. So now when I look at this, the only thing I can do is factor, so I'm going to get arctan x plus ln of x all over x minus 2 x plus 2. So nothing cancels out, no whole. Piecewise would be the one that would give us the jump. And then, so it's going to have to be infinite here. So set both is equal to 0, so x equals plus or minus 2. But we can't use negative 2 because it's not on my domain. All the domains have to align. So it worked for tan x, it works for this x squared minus 4, it does not work for ln of x. So we cannot use negative 2. The only answer we can use is x equals 2, and that's going to be infinite. And that's going to wrap up continuity.